Welcome to day 4, polar coordinates. We're going to do something a little bit different today. We've been used to doing everything in what we call the Cartesian coordinates, or rectangular coordinates, or what we call the XY axis, called the Cartesian plane. Today we're going to do things on a polar coordinate grid. It's going to look like a dartboard or like a radar screen if you're on an airplane or if you're an air traffic controller. So first of all, let's plot the point 7, 4 and call this point A. Well, that's pretty easy. 7, 4. Right here, 7, 4. And I'm calling it point A. So I said, give me another ordered pair for this point A. I don't know. What can I do? There's only one way to do it, and that's just call that point 7, 4. That's it. So what makes Cartesian or rectangular coordinates so special? There is only one way to name an ordered pair, and that's going to be whatever x and y that it has. There's no other way. You can't switch things. You can't do this. You can't do that. There's only one way to do it. So instead of doing Cartesian or x and y's, we're going to do polar coordinates. It's a different way to grab points, and we're going to use this grid that's on the bottom here. Like I said, it looks like a dartboard or a radar screen. Instead of doing x's and y's, we are going to graph r's and thetas, where r is a radius or a length and theta is an angle on the positive x-axis. So again, the radius is going to be the length from the origin or the center, and the theta is going to be the angle of rotation. And the circles, these concentric circles, represent a radius length from the center. So it's like 1, 2, 3, 4, 5, 6. And these lines that you see here are the angle lines that represent 15, 30, 45, 60 degrees. So we have two ways, we have a couple ways that we can plot things. One way to plot things is to do the radius and rotate. So that means I would go from the center, I would go out, and then I would rotate. I would do the r first, and then I would do my theta. And I have my r comma theta. Or another way, and I tend to do this more often, that's just the way my brain thinks, is that I go find the angle line first. So I find this angle line first, whatever I want, and I start from the origin, I go out that radius. So this is my theta line first, and then I get my r theta. It's up to you. It doesn't really matter. So for an example, 5, 60. You can go out 1, 2, 3, 4, 5 and rotate to 60 degrees. Or I find the 60 degree angle line and I go out 1, 2, 3, 4, 5 circles. There's my point A, and that is 5, 60. Now it says, give another ordered pair for this. Well, the one thing I do know is that I can keep on going around and around and around. So this angle here is not only 60 degrees, but if I add another circle to it, it's also 420 degrees, 780 degrees. And if I go backwards, I could subtract 360 degrees. So it's also the angle negative 300. They're all the same location or the same angle line. So I have 5, 420, 5, 780 degrees, and 5, negative 300 degrees are all the same point as that one I did in blue, 5, 60. Is there a problem with this? Yeah, there's a problem. There are infinite ways this can be done. I could keep on adding and subtracting full circles to all of this. So my summary is, if I have a point, r theta is given to me, and I want the same location, but I want a different name, I could take the r and either add or subtract 360 degrees to that theta. It's going to give me the same point as before. So this has many, many, many names. So is it possible to have a negative radius? It doesn't seem logical that you could have a negative radius, but you can with polar coordinates. So you can have a positive and negative x values. On the Cartesian, you can have a positive and negative r's and thetas in the polar grid. So how is this done? Well, one way to do this is to start here and go backwards 6. 1, 2, 3, 4, 5. There's negative 6. And then rotate 30 degrees from there. And that would be 30 degrees right here, because you start at the negative x-axis. So this is point B, which is -6, 30 degrees. Okay. Here's another way it could be done. Another way is, I'm going to use blue for a second in the eraser. Here's my 30-degree angle line, which is right here, across from it. The 210 to 30 degree is all the same line. So if I go 30 degrees, I go positive 1, 2, 3, 4, 5, 6. This is positive 6, so I would have to go backwards. So do a negative radius, give me going backwards, so I would have to go backwards 1, 2, 3, 4, 5, 6, and I get the same spot as I had before. But if I look at this point, I can name it a different way. Instead of using this -6, 30, I could realize it's positive 6 and it's been rotated 210 degrees, so 6, 210 degrees, or on the 210 degree line is a positive 6, or not only is it 210 degrees, it's negative 150 degrees, so it could be positive 6, negative 150 degrees. So if you notice here, what's going on, r comma theta, if I want the same location, becomes negative r. Ooh, what the heck happened here? Okay, sorry about that. So r theta for the same location would be negative r, the opposite of r, but instead of plus or minus 360, which is a full circle, I have to do plus or minus 180, which is a half a circle. So basically all year we've been working in ordered pairs, x's and y's, or the Cartesian plane or rectangular coordinates. And when we've done things in our calculator, we've been in that mode, function mode, and we've been doing y as a function of x, and we've been doing this all year, even when we did sequences, even though we could have done something else, but this is fine. Now we're going to change our calculator. We're going to change the way we're going to do things. We're going to do, our calculator is going to be changed to polar mode, especially tomorrow when we start really using our calculator to do things. And now, instead of saying y is a function of x, r is a function of theta. It's a little bit different because we're used to being over here, x is in and y is out. And over here you think, well, r should be in and theta should be out. It's the other way around. Theta goes in and r comes out. And we still graph these ordered pairs as r comma theta, but this is the way it's done. It's a very interesting process, and not everything we're going to draw is going to be a function. We could draw circles, we could draw, well, you'll see what we're going to do tomorrow. So it's all based off this picture. If you notice, we have one point on the graph, x comma y, or r comma theta. X and y is the horizontal and the vertical distance, and r and theta is my distance r from the origin and my angle of rotation. And to me it looks very similar to something we've been doing for the last 3 days. So this picture that is drawn up here on top and the one I just drew, they're basically the same picture, except the blow up one has vector v is the radius r. It's the only difference, but it's really the same idea. Okay, so we're going to work on conversions. Sometimes we have x's and y's and we want r's and thetas. So my Pythagorean theorem, my definition of tangent in a right triangle, or better yet, you can use these two, which we've been using for vectors the whole time, except that we've been using a little bit different letters, but the same idea. And if we have r's and thetas and we convert it to x's and y's, well, again, this is really the same two equations. Oops. This is really the same two equations we've been using to go from to get the x and y component for a vector. Okay, we do have to be careful a little bit. We have to make sure that we have to pay attention to the quadrant. Let's see if this works out okay. We have to make sure our theta matches whatever we want for the quadrant. We're not going to do radians at all, so remember we could do add or subtract 360 or add or subtract 180 if we want to make a negative r, and so on and so forth. So we're using these 4 equations, which are exactly the 4 equations we've been doing for vectors. So for the next set of problems, I'm giving you an x and y value, we're going to convert them to r's and thetas. The first thing we're going to do is use those equations on the top of the page to convert into r's and thetas right here in the red box. Make sure we match the quadrant, and then we're going to convert into a negative theta by subtracting 360 degrees from it. And then we're going to make a negative r, which means I have to add or subtract 180 degrees from that theta, and so on and so forth. So let's go to it. It's not that hard. 3 4s in quadrant 1, I'll make note of that. R is equal to 3 squared plus 4 squared square root of, which is 5. Theta is inverse tangent of 4 over 3. And for right now, for the moment, I'm only going to use to the nearest degree. 5, 53 degrees. 53 degrees is in quadrant 1. I'm happy. Now I'm going to convert them to the others, so it's still going to be positive 5, except now I'm going to subtract 360 from this angle, and I get negative 307 degrees. And then the last one, I'm going to make it a negative r, so it's going to be negative 5. I could either add or subtract 180 degrees from the original 53, so I'm going to add 213 because I decided to have a positive r, but you could have subtracted. It wouldn't have made a difference. For part B, negative 4 3s is quadrant 2. Again, for the radius or the length, I don't have to use negative numbers there because of the squaring part. So I just did 4 squared plus 3 squared square root of, which is equal to 5. I did inverse tangent of the y over the x. I do have to use negative numbers here. Negative 37 degrees is in quadrant 4. Doesn't match up. Add 180. So my angle is 143 degrees. 5, 143 degrees, which is in quadrant 2. And I can convert the rest. So you see I went ahead and finished up all the rest of the work. Notice I always had to match the quadrant. So in part C, I had to add 180 degrees again. In part D, I had the quadrant matched, but I could add 360 if you don't like that negative 27 degrees. For the middle column, I just subtracted 360 from the theta. And in the last column, I made the r negative, and I either added or subtracted 180 degrees to the original theta to get the angle I wanted. Now we're going to plot all these points. I'm going to take all these points, x's and y's, r's and thetas, x's and y's, r's and thetas, for all these points, and I'm going to put them on the grid. The Cartesian is going to be really easy to do. So on your paper you can look at them. I'm going to scroll up. So you can see plotting these x and y's is really easy. The first point was 3, 4, and you see in quadrant 1, 3, 4, B was negative 4, 3, C was negative 5, and D was 6, negative 3. Really easy to do. Now I'm going to move to the right and do it on the polar grid on all the polar coordinates that we had in that first column that we filled out. So you can see I marked A, B, C, D on the polar grid. A was 5, 53 degrees. 53 degrees, I had a mark in between 45 and 60. And I went out 5. B was 5, 143 degrees. I had to do the same thing, mark 143 degrees. And I kind of went out 5. C was 7.1 to 25 degrees. And D was 6.7. And 333 or negative 27 degrees, which I had a mark. If you really compare these two, don't you think those 4 dots in red look exactly in the same location as those 4 dots in blue? If you could pick up the one grid and lay it over the other grid and mark and lay the centers or the origins on top of each other, those points would be on top of each other. Okay, I'm going to give you an r and a theta, and first we're going to convert it to a negative r by subtracting 360. Excuse me, a negative theta by subtracting 360 from theta. And then we're going to do a negative r by making a negative and doing theta plus or minus 180. And then we're going to convert it to x's and y's by using x equals r cosine theta and y equals r sine theta, and we're going to round to 110. So the first one's pretty easy. Subtract 360 from the theta. I get 5, negative 240 degrees. Second one is again pretty easy. 5 becomes negative 5. I take my theta, either add or subtract 360 or 180. I'm going to add 180 to keep a positive r. And over here I'm going to do x equals 5 cosine 120, y equals 5 sine of 120. I'm going to go to my calculator, and when I put that in the calculator, I get negative 2.5, 4.3, That's in quadrant 2, and I'm pretty sure that angle's in quadrant 2, so it's all good. Okay, I'm going to probably pause my video so I could do the writing off camera. So you see I did part B and part C. The ones in red, I just took my theta, subtracted 360. The one in blue, I took R, made a negative, and either added or subtracted 180 to the theta. And for the pink, I did my X is R cosine theta, and my Y is R sine theta. And I went to my calculator, rounded to 1 degree, and you can see that this is in quadrant 3, negative, negative. Quadrant 3, this is in quadrant 4, positive, negative. And that's in quadrant 4. So you can see I did the rest of the letters C through H. Obviously the red has a negative angle, the blue has a negative R, and the pink are the X's and Y's. And I'm going to go below on the grid here and plot all the letters A through H using the original point that was given. So there are all the 8 points with the letters by them. Sometimes you do have to estimate where they're at because 2.7, 90, 2.7, you know, you have to estimate 2.7 above that axis, and so on and so forth. And if you look at all the quadrants on here, and the quadrants of the angles, and the points that were in pink, they should all match up.